Welcome to In Depth with Academia. This is Richard Price, your host and the CEO of Academia.edu. Hey there, thanks for tuning in. It's great to dive deep into academic research and, peel back the layers of these fascinating studies together. How's everyone doing today? So today we're exploring a pretty hefty topic, but it's really fascinating. It's a paper by Taoufik Amaloui titled A Closed-Form Analytical Solution to the Complete Three-Dimensional Unsteady Compressible Navier-Stokes Equations. Quite a mouthful, right? So let's just pause and think for a moment about what we're diving into here. Ever wonder how air dances around the wings of an airplane or gushes seamlessly through pipes? Or, how it whips around a rugby ball during a crucial pass? Well, that's where the Navier-Stokes equations come into play. These equations are the backbone, no, the very DNA of fluid dynamics. The Navier-Stokes equations. Oh boy, there are these complex puzzle pieces of physics that attempt to describe the motion of fluid substances like gases and liquids. Our core question here is all about finding a solution. No, the solution, one that actually works across these complexities. Why so significant, you ask? Well, because understanding these, or better yet, solving them, could have huge implications for engineering, meteorology, oceanography, pretty much anything involving fluids in motion, actually. Amaloui has tackled this head-on, looking into a refined potential theory for these equations. What's he done exactly? He's introduced something called the Poisson function. It's a fancy term for a viscous potential stream function, aimed to capture, and I mean truly capture, the unsteady features of real-world flows. We're talking flow separation, vortex shedding, a plethora of dynamics traditionally modeled by very complex numerical simulations. So what do these terms mean? Imagine how air might flow over a car's side mirror, or how it behaves when swirling down a bathroom sink. The Poisson function aims to model that more accurately, but in, an elegant mathematical way. What's the magic sauce in Amaloui's research? The key is combining the properties of potential functions to satisfy inertia terms of the NSE, or Navier-Stokes equations, and integrating features of a stream function to meet the continuity equation. It's like the marriage between two theoretical principles, making way for a breakthrough. Yep, that's it. RPT, or refined potential theory, bridges this gap between classical theory and real-world applications. So it's like taking something theoretical and giving it real-world traction. Okay, let's groove on to the concept of turbulence. Have you experienced it, say, on a flight, where the plane rocks a bit due to irregular air motions? This research explores capturing turbulence within streams, without adding complexity to already heavy computational models. This Poisson function, it's, how should I put it? It's like it is a simpler path to understanding this chaotic flow, and a big shout out to the methods. Amaloui uses experimental data alongside numerical experiments to verify the predictions made by his models. It's crucial to stress, though, that while the Poisson function offers intriguing insights, it's essential to view it as one innovative approach among many in the vast space of fluid dynamics, a piece of the puzzle, if you will. Nothing in academia is set in stone, and that's part of what's so invigorating about these discussions, and here's where it gets even cooler: the validation against experimental and numerical data for flows on objects like, wait for it, circular cylinders, spheres, and even spheroids. Yes, a step in validating the potential of this theoretical model compared to real-world data. I mean, trying to perfectly predict such natural phenomena is like catching butterflies with a net made of equations. So, what does this mean for you, our inquisitive listener? Whether you're involved in engineering or just fascinated by the mysteries sketched by science's abstract ideas, this work, it invites you to reconsider the frameworks and hypotheses on fluid behavior. Trust me, the ripples could affect how future technologies evolve and complement the natural world. Phew, I've thrown a lot at you just now, haven't I? Research like Amaloui's is an eye-opener, a reminder that, even when equipped with the finest tools, understanding the universe remains an ever-persistent exploration. Remember, these papers and findings are insights to digest, not absolute truths etched in stone. We've reached our denouement here, and wow, what a ride. Thank you for tuning in to In Depth with Academia today. Please feel free to explore this paper and others on Academia.edu for, a deeper dive. Until next time, keep questioning, keep exploring, and take a moment to appreciate the splashes of wisdom these brilliant minds have to offer. Stay curious, everyone, and take care until our paths cross once more.